Hi there, and welcome to this lesson on Further Pure Mathematics 2. And in this lesson, we're on Chapter 8, 8.2, and we're looking at curve sketching with polar coordinates. There are two approaches to curve sketching with polar coordinates, and they're exactly the same as the two approaches that you're already familiar with from curve sketching with Cartesian coordinates. So first of all, it is possible to calculate the position of various points which lie on the curve, to plot those points, and then join them together to create the curve. Now, to do this, it is helpful if you have polar graph paper, which looks something like this. Distances from the pole are measured off in units, and angles from the positive x-axis are measured, in this case, in multiples of pi by 24 radians. It isn't essential, and for the curves that we're looking at in this lesson, you won't need any. The other thing you can do is learn or predict the general shape of a curve by getting to know the equation by considering the equation. So if you have something like 3x squared plus 2x plus 4, you're familiar with the equation and you're also familiar with what quadratics look like. You can do the same thing with polar curves. Now we're going to meet quite a lot of different types of polar curve today, and there is real value in you just noting them down and trying to learn the general shape of certain curves. Okay, three standard curves for you to have a go at yourself. So I'll say nothing about these. See if you can work out yourself what these curves will look like. So pause the video, have a go at them, and then come back to me when you're ready. Okay, let's have a look. So first of all, r equals 4. That's saying you've got a point, and the point has to be 4 units from the pole. And the question is, what shape will that describe? Well, you'll get a circle with center the origin and radius 4. In general, r equals a, where a is any constant, describes a circle, center the origin, with radius a. Now, since we're talking about circles, there are two other formulas for circles that frequently turn up, and it is worth learning them. R equals 2a cos theta is a circle with center on the x-axis at a0 and with radius a. So, for example, if you had the equation r equals 4 cos theta, halve the 4 to get 2, and that'll tell you where the center is. The center is at 2, 0 on the x-axis. It'll also tell you the radius of the circle. The circle will have radius 2 and touch the origin here. And in a similar fashion, r equals 2a sine theta is also a circle with center on the y-axis at 0a and again with radius a. The second question, theta equals pi by 3. What is that saying? Saying there's a point, and if you join that point to the pole, the angle between the line and the positive x direction should be pi by 3 radians. So the point could be anywhere on that line where the angle between the line and the positive x direction is pi by 3. Now you'll notice it's a half line, so it doesn't go this side of the pole, it begins at the pole and then heads in the angle given. And in general, theta equals alpha describes a half line making an angle of alpha with the positive x direction. The third one, r equals 4 theta, a little bit more tricky this. We'll consider what happens as theta increases from 0 to 2 pi. When theta equals 0, r equals 0. So the curve begins at the pole. And then as theta increases, so does r. So as theta gets bigger, r gets bigger and bigger, and we get further and further away from the pole. That'll give us a curve something like this. And in general, r equals a theta describes a spiral starting at the pole with crossing points on the axes given there. Okay, example 2. This time we are going to draw a table, plot the points, and then try and guess what the right way is to join them together. So complete the table, plot the points, and then see if you can work out how you should connect them. I'll let you have a go at doing this. Pause the video, come back to me when you're ready. Okay, let's have a look. First of all, completing the table gives you those values, and if I then plot those points, I'll get this. Now, it's not many points there, and the question is, what's the right way to join them together? The curve starts at 0, 4. That's this point here. And it will be a curve. It's not going to be a series of straight lines. And also, you would expect the curvature to change smoothly, for nothing very abrupt to happen to the curvature, except at exceptional circumstances. So we're going to start here. There should be a smooth curve round to 2. The curve should continue to be smooth till it takes us round to 0, and then around to -2, and then back here to 4 on the x-axis. The curve looks something like that. Now, in general, if you have r equals any number a into 1 plus cos theta, you'll have a curve with this sort of shape, and it's called a cardioid, where cardioid means heart, because the curve has a heart shape. And the crossing points will be a and -a on the y-axis and 2a on the x-axis. There is a special point on this curve here at 0, where the curve dips in. And at this point, the curvature is not continuous. So we come into a sharp point and then go out again. It's worth noting that the function is of cos theta alone. So we've got r equals f of cos theta. The significance of that is that because cos theta equals cos minus theta, the curve r equals any function of cos theta will always be symmetrical about the x-axis. So you'll notice that the top is a reflection of the bottom here, and vice versa. That is always the case as long as the function that you have is only a function of cos theta and nothing else. There are 4 possibilities for a cardioid. R equals a plus or minus a cos theta will give you a cardioid, and also r equals a plus or minus a sine theta. They all look the same, it's just the orientation that changes. So r equals a plus a cos theta is like the one we just drew. If you change it to minus a cos theta, it reflects it in the y-axis. R equals a plus a sine theta is a vertical heart that would look like that. And r equals a minus a sine theta reflects that in the x-axis. And you get a shape that actually does look a bit like the conventional way of drawing a heart. Now, r equals a into 1 plus cos theta is itself a special case of the general form r equals a into p plus q cos theta, where p and q are different numbers from each other. If p equals q, then you have the heart shape, you have a cardioid. Otherwise, there are 2 possibilities where p does not equal q, these 2 numbers here in the brackets. The first possibility is that p is bigger than q, but it's less than 2q. Now, if that's the case, you get an egg shape with a dimple. Looks a little bit like the cardioid does. So, for example, if you had a equals 1, q equals 4, and p equals 5, then p is bigger than q, and it's also less than 2q because it's less than 8. And in that case, you'll get a curve like this. At first glance, it looks exactly the same as the cardioid. The significant difference is this point here, which is no longer a sharp point where the curvature changes abruptly. What you would have here is a smooth point with constant curvature. The other possibility is that p is bigger than q. Now, if p is bigger than q, but it's not less than 2q, then you still get this same sort of shape, but this dimple here vanishes completely. So, for example, if a was 1, and q was 2, and p was 4.5, then 4.5 is bigger than 2, but it's not less than double 2, it's not less than 4. And you can see here the dimple just vanishes completely, and you have this sort of egg shape. These curves all have a special name. These curves are all called Limousines. And as we said, there are 2 possibilities for this shape, either the egg shape with a dimple or the egg shape without a dimple. Example 3 is one of those possibilities. Have a go at completing this yourself. So finish the table and then just do a rough sketch of what you think the curve looks like, indicating where the x and the y axes are crossed. Okay, pause the video and then come back when you're ready. Okay, let's have a look at this. So in this instance, 7 is bigger than 3, but it's not less than 6. So we'll get an egg shape with no dimple. Those are the 4 points that I've calculated from the table, and those will give me the crossing points on the axes. So the first one here is at 20 on the x-axis, 14 here when we get round to 90 degrees. You'll notice here that it says 8. It is minus 8 on the x-axis, as you would use x-coordinates. The 8 is the distance, which is why it says plus 8. And same with the 14 down here. The distance is 14, but it would be minus 14 on the y-axis using y-coordinates. Part 2, sketch r equals a into 6 plus 4 cos theta. So same as before, fill in the table and try and do a rough sketch, but indicating where the curve crosses the axes. This time we don't know the value of a, by the way, so you'll have a in the table, and you'll also have a included when you do the crossing points on the axes. Anyway, pause the video, have a go, and come back when you're ready. Okay, let's have a look. So as we said, the values in the table are all multiples of a, 10a, 6a, 2a, and 6a. This time 6 is bigger than 4, and it is less than 8. So we will get a dimple this time. And it'll look something like this. This crossing point here would be 10a, this would be 6a, this would be minus 2a, and this would be minus 6a. The closer P is to Q, the more it looks like a cardioid. And the further away P and Q are from each other, then the less it looks like a cardioid. As with cardioids, there are 4 possibilities for the orientation of a limousin. So you can either have plus or minus Q cos theta or plus or minus Q sine theta. And just remember, if it's a function of cos theta, then the x-axis will be the line of symmetry. If it's a function of sine theta, then it's the y-axis that will be the line of symmetry. Okay, example 4, much bigger table this time. Sketch the curve r equals 2 sine 3 theta. So first of all, fill in the table. This question is quite tricky to do without proper polar graph paper, but try and roughly plot the points as best you can and take a guess at what it looks like when you draw the curve. Now, I'll give you no further hints than that. So see if you can work your way through this, pause the video, come back to me when you're ready. Okay, let's have a look. Quite a bit more tricky, this one. So first of all, filling in the table will give us those values. A lot of repeated values there, which suggests there's going to be a lot of symmetry in the curve. And the other thing to note is we've got negative values in the table. But r is a scalar quantity, r is distance. And therefore r has to be positive, which means if ever you're doing a table and you get negative values, you discount those values as being impossible. So we'll get rid of all of the negative values. The second thing is, having done that, the table does suggest that there are going to be 3 separate parts to the graph. This part, then a gap, the second part, then a gap, this part, and then a third gap. So it looks like 3 parts and 3 gaps. And lastly, we've got a function of sine theta, because you've got f of sine 3 theta. And as we said before, because sine theta equals minus the sine of minus theta, the significance is, if you have a function of sine theta, the curve will be symmetrical about the y-axis. So if it's a function of sine theta, symmetrical about the y-axis. Now that is what the curve looks like. So these first set of values here from 0 up to pi by 3 radians take us from here, going from 0, going to a maximum distance here of 2 from the pole, and then coming back in again. And then we've got this gap here where we had negative values for r. That's the gap we have here where the curve is not defined. And then from 2 pi by 3 up to pi, the curve is defined again, and we get the second loop. Then we get the second gap, which is why we get a gap here. Then we get the third loop, which is this loop at the bottom. And then the third gap, which is the gap that takes us back to the beginning again. Now, in general, curves of the form either r equals a sine n theta, where n is a positive integer, and r equals a cos n theta, where n's a positive integer. There are two possibilities. They will either have n loops symmetrically arranged around the origin if n is an odd number. But if n is an even number, you actually get double the number of loops, again symmetrically arranged around the origin. Curves of this form have a special name. They're called rose curves. So r equals 2 sine 3 theta. Because 3 is an odd number, you get 3 loops. So 3 theta means you'll get 3 loops symmetrically arranged. 5 theta, you'll get 5 loops. 7 theta, you get 7 loops. But note, when r is equal to 2 sine 2 theta, because 2 is an even number, you're going to have to double it. So instead of being 2 loops, you get double 2. You get 4 loops symmetrically arranged. Okay, example 5. That's the curve that we just drew, r equals 2 sine 3 theta. And the question's saying, well, if that's what 2 sine 3 theta looks like, what will r squared equals 4 sine 3 theta looks like? So we'll square root both sides, and then we'll end up with a very similar curve. But the question is, what's the difference? It will be extremely similar, but in what way will it be different? I'll let you have a go at guessing that or working it out yourself. So pause the video and then come back to me when you're ready. Okay, r squared equals 4 sine 3 theta. Square rooting both sides would give me r equals 2 square root sine 3 theta. Now that's the same as we've got here, except instead of sine 3 theta, we're going to have to square root it. Well, that's going to be a number between 0 and 1. And if you square root a number between 0 and 1, it gets bigger. So r equals 2 square root sine 3 theta will have the same shape as that, but everything will be a little bit bigger. So you'll notice that the loops are fatter than they are in this example. That's the only way in which it changes. Example 6, again, starting with r equals 2 sine 3 theta. The question is, well, what will r equals 2 cos 3 theta look like? Again, I'll let you have a go at working this out yourself. So pause the video and then come back to me when you're ready. Well, r equals 2 sine 3 theta. Because 3 is an odd number, there are just 3 loops symmetrically arranged. Because it's a function of sine theta, it's going to be symmetrical about the y-axis. And you can see that the y-axis is a line of symmetry. R equals 2 cos 3 theta. Well, that's a function of cos theta. Because it's a function of cos theta, it'll be symmetrical about the x-axis. Now, I think the easiest way to get these started right is to think what happens at 0. Now, if I put theta equals 0 into 2 sine 3 theta, 2 sine 0 is 0. So when theta equals 0, r equals 0. And it starts out from here. That's not the case with cos. If I put theta equals 0 into cos, the cos of 0 is 1. So r equals 2 cos 1. R is going to equal 2 when theta equals 0. So when theta equals 0, r equals 2. And that would be the starting point. And that's how the 3 loops are arranged. Now, there is a close link, as you've probably already guessed, between the loci of complex numbers and polar curves. Example 7. Show that the locus of the points given by the values of z which satisfy the modulus of z minus 6 minus 8i equals 10 can be represented by the polar curve r equals 12 cos theta plus 16 sine theta. Okay, if you can remember your complex number work, I'll let you have a go at doing this yourself first. So see if you can work your way through this question, pause the video, and then come back to me when you're ready. Okay, let's have a look. Well, the best approach to this is really saying that z minus 6 minus 8i, it's the same thing as z minus, and we put brackets 6 plus 8i, equals 10, that represents a circle with center 6 plus 8i and with radius 10. That means we can immediately say what the Cartesian equation of the circle is. The Cartesian equation of this circle will be x minus 6 squared plus y minus 8 squared is equal to 10 squared, which is 100. Then all we have to do is what we were doing before, which is substitute x equals r cos theta and y equals r sine theta into this equation. And that'll give us r into cos theta minus 6 all squared plus r sine theta minus 8 all squared equals 100. Multiplying out the brackets will give us that. Collecting together the cos squared and sine squared here gives us that. The reason for doing that is because cos squared plus sine squared equals 1. So that will simplify to r squared equals 12r cos theta plus 16r sine theta. Then we could divide through by r, and that gives us r equals 12 cos theta plus 16 sine theta, which is what we were asked to find. Okay, that gets us to the end of this lesson. If you've got the textbook, then turn to page 157 and have a go at exercise 8b. Thanks very much for listening, and cheerio.